All right, I think we both knew that this time had to come. I'm going to give you a little bit of information about the electric potential of a point charge. This is problematic because unlike a parallel plate capacitor, where we've got a uniform field, a point charge has a field that is dramatically weird. I mean, let's just throw an electric field of a point charge here. Let's say that this is some charge, positive Q, then it's got electric field that's coming out from it in all directions and noticeably getting weaker in all directions, and the direction of the field depends on where the heck you are and really how far left you are, how far up you are. It depends on all kinds of things. And the strength of it can be indicated by the density of this field line. So really close to the point charge, you've got a strong field. And really far away from the point charge, you've got a really weak field. So it's so different than this uniform field that you might have inside of a parallel plate capacitor or a similar setup. So our issue will be, how do we address this potential of a point charge? And I'd like to go all the way back to Coulombs Law, which says that the electric force between two charges is Kc times Q1 times Q2 over r squared. And I suppose there's an r hat vector here which says that the force is outward when the charges have the same sign. So the force is away from Q1 and Q2. They repel if they have the same sign. And if they have opposite signs, then this force would be in the negative r hat direction. So it would be inward and therefore an attractive force. Once we have the force though, we've got a force and we want to get to energy. Well, I remember that work is the integral of force over distance. There's probably a dot product in here. We've got to multiply those suckers. So if we're talking about change in electric potential energy, then we're going to have to integrate that sucker. And so I will write change in energy is the integral of electric force, maybe dr. And I'm going to talk about going out away from the origin. Let's make this a little bit more concrete with actually setting a charge here. We'll need this picture on the next diagram as well, so I'll have to do that there again. But I want to put some charge here. Let's say I put positive Q right there, and I'm going to put another charge over here at some location, and we'll call it Q naught. It's assumed to be positive, so just make it explicit. And this distance right here, because I'm going to call that location A, and I'll probably want a location over here labeled B in a little bit, because I'm calling it location A, I can then show this distance as r sub A, and this distance here will then be r sub B. I think to put it on there would just clutter my picture though. Okay, if I'm going away and the force is in that same direction, then the change in energy, the change in energy ought to be negative, because you remember there's a difference between work and change in energy. There's got to be a minus sign right there. So I'll just slip that right there. And what we'll do is we'll plug in this expression for the electric force. It's Kc times Q1 times Q2 over r square, and then there's this r hat direction of the electric force, but that's dotted into dr, so that's lovely. It's simply an integral over dr, and the vector character of it is gone. Now I'm going to pull out all the variables that are constant over r changing, and that includes Kc. We still got a minus sign. It's Kc and Q1 and Q2. None of those change depending on where you are. Those are still the quantities of charge and the fundamental constant of nature, Coulomb's constant. And then I need this integral, which is dr over r squared. And that integral is the same thing as this integral is the same thing as the integral of x to the negative 2 dx. So we can evaluate that sucker. You remember what x to the negative 2. I suppose if you're integrating things, you're supposed to raise the power of it. So this is x to the negative 1, and then you're supposed to divide by the new power, and we'll just put a minus sign in front of it. So if I do all this integration, I should get negative Kc times Q1 times Q2, and then, well, I've got this other thing here, this R2 to the -1, and then I also have to multiply by -1. So let's clean all of this up, and I'll get positive Kc times Q1 times Q2 over R. And I suppose I need to evaluate both of these things between, what? Location A and location B. If I'm going from location A to location B, then that's what my integral is. It's from location A to location B. And I'm talking about the change in energy between Q0 moving from A to B. Do you expect that the energy will increase or decrease as that happens? Well, that's an interesting question. The energy at B should be less than the energy at A. So if I subtract the energy at B minus the energy at A, that's what this limit says right here to do, B minus A, then I'll get a negative change in energy, which is consistent with the fact that potential energy has been lost if the charge moves from A to B. Because it's moving the way it wants to go, energy is lost. Cool? So this is then simply Kc Q1 Q2 over Rb minus Kc Q1 Q2 over Ra. Sorry about the formatting there, that's a mess. But there's something lovely about the change in energy. We can define the energy to be 0 at a particular point. Nah, let's not do that yet. Let's not do that yet. Here's what I want to do. I want to now go from, we've already gone from force to work and energy. We can now go from energy into potential, because that's really our game. So in order to go from energy to potential, all we have to do is divide out by the charge that is feeling the force. And in that case, well, of course they're both feeling the force. That's stupid, right? But in this case, since we're moving Q0, we can say that this Q at the origin is creating the force, and this guy is the one that, in this case, we're studying to be feeling the force. So I'm going to cancel out a Q0. To do that, I need to be a little bit more explicit about what Q1 and Q2 are. I'll change this guy to just Q, and I'll change this to Q0. So this is simply Q, I'm crossing it out, and that's Q0, that's Q, and that's Q0. So I'll transfer to a new page. And I find that the change in energy is, well, it's Kc times Q, Q0 over Rb minus Kc times Q0 over Ra. And to remind you, we had a charge at the origin that was Q and a charge over here that was going from A to B, and that charge initially started at A and it was Q0. So we had some distances, and you notice that Ra is smaller than Rb, so we're going to have this be a larger number than that, so we're going to get a negative. Let me just label that there. The change in energy is less than 0 as it moves the way that it wants to go. Reasonable, I think. And now we know that potential, let's be explicit, it's change in potential is change in potential energy divided by charge, and we're going to divide by Q0 to do this. So that's simply Kcq over Rb minus Kcq over Ra. Ooh, interesting. The wonderful thing about this is that potential is arbitrarily defined. It's about change in potential that we're interested. So I want to point out to you, first of all, as Rb approaches infinity, what happens to the potential at B? I would argue that Vb goes to 0. Okay. So now we can argue that the potential of a point charge, the potential of a point charge is simply, wait, are we supposed to go from A to B? Oh, shoot, all this is a mess. We're supposed to go from B minus A minus B, minus sign, blah, 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 minus sign. Okay, so I want to argue finally that the potential at a point, no longer the change in potential, but the potential at a point is Kc times the charge that's causing the potential divided by how far away from that charge you want to know the potential. So if I want to know the potential at A, I plug in R sub A right here. If I want to know the potential at any arbitrary location, I just need to know Kcq over R. Now the issue is, this is not a vector. That sucker is a scalar quantity, and you know with electric fields you have to use the principle of superposition, or the Newton avoid the bully kind of principle. So in this case, we're simply adding numbers. If you've got a charge here, and a charge here, and a charge here, and you want to know the potential over here, all you need to do is find the distance from Q3 and the amount of charge that's at Q3 and get yourself some potential, and do the same thing for here, that distance and that charge and that distance and that charge, and add them together. Wow! Wow! R is always a positive number because it is simply a distance. It doesn't have anything to do with which side of it you're on. And this is simply a scalar, so it doesn't have any direction. But Q, if one of these charges were negative, it would reduce the potential at this location right here. In fact, if there's only one negative charge in the whole universe, let's put it here. Clean universe. Only one charge. This is Q4, and Q4 is less than 0. So everywhere around it, V is less than 0. Everywhere around it, there is a potential that's less than 0. In fact, if we were to study this potential in more detail, we'd find that the potential is everywhere kind of falling into, whoa, and there's this really beautiful graph that you can see if you were able to make cool pictures. But the potential is kind of like the graphs that you've seen of a black hole and space-time curving into it. That's a little bit more of an advanced topic, but if you can imagine curving these things, then you make what's called equipotentials on here, and you see that they get closer and closer together as you get closer and closer into the center of that charge itself. And the potential at the charge is negative infinity, if you can get that close. But you probably can't get that close. But the point is, if you can get exactly on top of a charge, the potential there would be negative infinity if it's a negative charge, and positive infinity if it's a positive charge. So we can look in one dimension. It's too confusing to look in 2 dimensions like this, or trying to make a 3-dimensional graph on a 2-dimensional sheet of paper. But I want to take a slice like this way. Let's imagine whoosh, I slice the paper like this, and then I can show you, here's a negative charge, Q is Q4, and I say Q4 was less than 0. And now I'm going to make a graph of the potential. So here's potential equals 0, and this is location, and this is potential. So you know that the potential is negative. Right on top of Q4 it's negative infinity, and nearby it it's doing something like this. And you know that on the other side it's going to do something like this, and of course forever and ever it will be not quite 0 asymptotically. And what if it's not the only thing in the universe though? What if there's another charge over here? Let's do it the same distance away, right? This is Q5, and it's the same quantity of charge as Q4, but it's positive. Ha ha ha. Now I'm going to draw Q5's potential in green, or there. So let's go, Q5 is going to have an always positive potential, but it will be very, very small over here and getting bigger, 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 bigger. In fact, potential will be infinite right there, and we'll come back down like this. Notice how those are very similar. But if I wanted to know the overall potential, because the overall potential, like for instance at the origin, the potential at the origin is simply the potential from this plus the potential from that. Don't say anything about direction because it's not a vector. But it will be a potential, and if these are the same distance and the same quantity of charge, one positive, one negative, then the potential at the origin will be 0. Now the potential here, of course, wins out because we're talking about almost entirely the green line, because the purple line doesn't have much to say over here. And then over here we're talking about almost entirely the purple line, because the green line doesn't have much to say over here. But my point is, the overall potential, this is the net potential, and the green is the potential from Q5, and what else do we have, a purple or something? Yeah, this thing over here. This is the potential from Q4. Yeah, you come into the room and you're surprised to find me talking to myself? Don't be. Okay, so that's what we're doing when we're adding potentials, and the cool thing is if I put more charges on here, all we'd be doing is moving these lines around a little bit, and there's really no problem to it at all. Enjoy. It's coming out from it in all directions, and noticeably getting weaker in all directions, and the direction of the field depends on where the heck you are and really how far left you are, how far up you are. It depends on all kinds of things, and the strength of it can be indicated by the density of this field line. So really close to the point charge, you've got a strong field. Really far away from the point charge, you've got a really weak field. So it's so different than this uniform field that you might have inside of a... All right, I think we both knew that this time had to come. I'm going to give you a little bit of information about the electric potential of a point charge. This is problematic because unlike a parallel plate capacitor, where we've got a uniform field, a point charge has a field that is dramatically weird. I mean, let's just throw an electric field of a point charge here. Let's say that this is some charge, positive Q, then it's got electric field dr, and I'm going to talk about going out away from the origin. Let's make this a little bit more concrete with actually setting a charge here. We'll need this picture on the next diagram as well, so I'll have to do that there again. But I want to put some charge here. Let's say I put positive Q right there, and I'm going to put another charge over here at some location, and we'll call it Q naught. It's assumed to be positive, so let's just make it explicit. And this parallel plate capacitor or a similar setup. So our issue will be, how do we address this potential of a point charge? And I'd like to go all the way back to Coulombs Law, which says that the electric force between two charges is Kc times Q1 times Q2 over R squared. And I suppose there's an R hat vector here which says that the force is outward when the charges have the same sign. So the force is away from Q1 and Q2. They repel if they have the same sign. And if they have opposite signs, then this force would be in the negative R hat direction. So it would be inward and therefore an attractive force. Once we have the force though, we've got a force and we want to get to energy. Well, I remember that work is the integral of force over distance. There's probably a dot product in here. We've got to multiply those suckers. So if we're talking about change in electric potential energy, then we're going to have to integrate that sucker. And so I will write change in energy is the integral of electric force, maybe